I'm stepping over the time a little bit, but let's stick with the presentation. It will have more interesting topics coming up. So, multi-rate signal processing is a very important technique used in the industry of, I mean, in any industry which is there for, which is having DSP application. This you will find multi-rate signal processing blocks there. We have to upsample or downsample the signals. Which finds extensive application in digital front ends, like I have talked about or explained in the GNSS signal processing or communication signal processing. So we have the need to denoise the spectrum, and this is what I have shown in this illustration here. So if you see, if you are sampling the signal exactly at the Nyquist frequency, which is 2 times the maximum signal frequency, then the whole spectrum is filled with your signal and the quantization or whatever noise the system will have. So, and the SNR, which is the signal to noise ratio of the system, will be the yellow area divided by the red area. Whereas if you would have sampled or oversampled the signal at 4 times the Nyquist rate, then your signal would the discrete signal or the discrete spectrum will only span from minus pi by 2 to plus pi by 2, but the yellow area is same because there is a FS term or the sampling frequency term which is multiplied in your sample frequency response. So your yellow area is not changing, but your signal is spanning only from minus pi by 2 plus pi 2. So what you can do is you can filter this spectrum out because this is the only desired spectrum. You can filter this out so that the red area will decrease. So the red area will only, so basically the noise power will decrease by half. So what you are achieving is you are oversampling the signal and you are reducing the noise power by half. So your SNR, which is signal to noise ratio, is increasing by 3 dB. So this is generally the signals are oversampled by a factor of 40 or 20 or 40 times. So you can, I mean, you can understand how much SNR improvement is possible by doing this oversampling technique. And then the signals are taken down to the required sampling rate by decimation and anti-aliasing filter in the DFE or digital front end, which I have been talking about. So this is a very important technique and it improves the SNR. Then for multi-rate signal processing, we have CIC filters that I mentioned earlier, which is the cascaded integrator COM filters, which are used for upsampling and downsampling. And these are very important linear phase filters. These are these have importance because of their hardware efficient design. There is no multiplication operation required in implementation of these filters. I'll be showing in the next slide. So if you see these decimators or interpolator CIC filters are made up of these 2 blocks, integrator and COM blocks, I and C. And these 2 blocks only have delay and addition or delay and subtraction. There is no multiplication. This is a huge advantage in for practical DSP processors. If we don't have to do multiplication, the speed of operation becomes very high. So I have shown here the decimator, which is decimating the signal or downsampling the signal by a rate R. The rate R here is 4. So you can see when we do decimation, the spectrum of the signal expands by the same factor R. And we have to do an anti-aliasing filter before doing the decimation. So we have to notch out, or we have to filter out the signal so that it can have only this much of frequency, and then when we are decimating, this will expand and become from minus pi to pi. So for that purpose, we have anti-aliasing filters, and what I have shown here is the comparison of CIC filter with 2, 5, or 10 stages. We can see with only 2 stages, the stop band attenuation is very low. It is somewhere around 12 dB or something. With 5 stage or 10 stage, we can see the attenuation is high. Stop band attenuation is high, but the distortion of pass band is also more. So this is a band of interest where our signal is present, and we would like to be this band to be as flat as possible. But as we are increasing the stages, the flatness is reducing more and more. So that's where the DSP engineer's job comes into play, and we have to basically optimize the performance by keeping the pass band response as flat as possible, but the stop band response or stop band attenuation as high as possible. So these kind of design parameters are defined by the application, and we have to optimize the performance using these calculations. So these kind of multi-rate signal processing concepts are very important in the industry, and this has very wide industrial use. So we have dedicated engineers which work on designing front ends and these kind of filters to get the desired response. The next or the second last technical topic would be stochastic signal processing. So any real-life signals are stochastic processes. Stochastic means that it has some probabilistic structure associated with them. It's never deterministic. We cannot say that. For example, any signal which is coming from a sensor is having a white noise, or as I'm speaking into the microphone, there is a background noise which is present all the time. So that's why it's a stochastic process, and the noise is random. It's changing. We don't know what the noise is coming. Sometimes it can be some people talking in the background, or some other appliance beeping in the background. Whatever noise it is, it's never deterministic. It's always random. So that's what we call as a stochastic process. But to work with this stochastic process, we have to make some assumption, like some stationarity assumptions. Two of the important ones are wide sense stationarity and wide sense cyclostationarity. So wide sense stationarity, I'll be showing illustration in the next slide, what it means and what are the processes which we can call as WSS processes. These are not, these assumptions are not out of this world. There are a lot of signals which can be assumed to be WSS process. Most important of them are the wide Gaussian noise process, which is the additive noise which gets added into our signals in every system. And this wide Gaussian noise is because of the thermal or the heat generated in the hardware or the chip, mobile phone, laptops, or any hardware. And then we have to understand what is the LTI system analysis of WSS process. What happens when a WSS process is input to the LTI system, and how we can characterize the output of such WSS processes. So this small illustration is there to show you when we call when we talk about WSS processes. So these are two WSS processes. These are two instantiation of a wide sense stationary process or wide Gaussian noise. I should be. These are specifically wide Gaussian noise which is present in the system. And why it is Gaussian, we can see from these histogram plots. So this is the stream of noise, just the noise which is coming in the microphone. And if we plot the histogram of these noise samples with time, this is changing with time. But if you see the probability or the histogram, which represents the PDF of the values, is always Gaussian in both the instances. The autocorrelation function is a delta function always. It's not changing with time. Even though the samples are changing continuously, the autocorrelation function is always delta for both. And it is called wide Gaussian noise because in frequency domain, so this is the power spectral density of the WSS process. So this you can see is white all through. So this is always white. White meaning it is approximately having the same frequency power in all the for all the frequencies. That is why we call it white. And we have practical, as I've seen, thermal noise at the receiver is a practical example of wide Gaussian noise. And then we have audio signal in short term. So speech signal or some music or audio signal which is playing is a short term WSS process. So if we take only a portion, small portion of the speech signal, it will be a WSS process. And then we take the next portion, it will be a WSS process. So these are very practical examples, and these find applications in practical life. Then there is a very wide application of measuring the black box system's frequency response. So suppose we have designed a DSP system, but we have to know what is the actual response of the system, whether it is matching with the design, what we designed or not. So what we do is we provide a WSS white noise to the system, and then we measure the power spectral density of the output of this system. So this expression which I have shown here is true only for WSS or wide sense stationary input to LTI system. So if we have LTI system and the input is WSS, then we can use this expression, and then we can find out the frequency response, at least the magnitude response of the filter. This I have shown in this slide here. So again, we have the wide Gaussian noise going in the system. This is our design system. We don't know what the system, I mean, we have designed it to be a band pass filter, but we don't know what exactly how it has been designed. So we gave it a wide Gaussian noise here, and we get some output. We measure the power spectral density of this output, and when and this use this expression, the power spectral density of the output divided by the PST of the input, under root of that is actually the magnitude response. So this is the magnitude response of the filter. So from this we can then see that the filter is a band pass filter, and there are some ripples on the pass band. So this kind of response is revealed by the this is where the this is one of the most widely used application of WSS process to know the black box system's transfer function. Okay, let's talk briefly about adaptive filtering techniques. So this will be our last technical topic presentation. Adaptive filtering is used for this is used for scenarios where the input is changing or the system itself is changing with time, and we have to adapt the processing parameters based on the changing input or changing system. It's like we have multipath fading scenario where the channel response is changing with time, and the filter has to adapt to the channel or the multipath scenario. So or in speech signal, like I'm speaking and there are some background noise which is changing with time, and the laptop or the microphone has to implement some adaptive filtering to continuously cancel out the noise. It has to estimate the noise first and then cancel it out and reduce the noise, and then give you the clean voice or clean speech signal. So this is where there are Wiener filters which are state of the art and currently very widespread used used in speech signal industry, speech signal processing industry. So let's see a typical example of Wiener filter denoising of a signal. So we have a noisy signal coming up from the microphone, and we detect there is a block which detects when somebody is speaking or there is a silence. If it's a silence, Then we perform the noise spectrum estimation. So as I'm speaking, I'm having some small pauses and small like I'm pausing for a split second and then starting again. And these pauses are detected by this signal activity detector. And when I'm pausing, there is only background noise which is present in the which is going into the microphone. So this noise spectrum estimator estimates that noise and then provides it with to this block. And here the noise signal is coming. So we are estimating the noise plus signal spectrum here, and here we are giving only the noise spectrum. And this block is basically canceling out the noise spectrum from the noisy signal and giving us the clean signal. So this is a like a small example of how the filtering will be done. So this is suppose this is the original waveform or original speech signal which is coming into the microphone, and there is a high there is some high frequency noise which is present in the background, which is corrupting the signal like this. So you can see that the input signal is completely embedded in the noise, and we cannot even make out visually that this is the same signal with noise in the red plot. We can implement and this noise spectrum will be changing with time. So I have shown just one instance of this noise. This can be like moving. So the spectrum of noise can be moving here. It can be increasing in frequency or decreasing in frequency based on time and based on what is happening in the background. And this block basically will keep on estimating that change. And then we can design a Wiener filter, adaptive Wiener filter of different orders. So I have shown two here. So one is a higher order Wiener filter with several number of taps, like 70 or 100 taps, and one with a very low number of taps of only suppose 2 taps or 3 taps, based on what kind of capability we have. So even with this small number of 2 or 4 taps of Wiener filter, we can see, I mean, the noise is mitigated. There is a notch here coming and mitigating the noise, and there is an attenuation because of these 2-3 taps. And we can see that the original waveform is starting to emerge from noise, even with this such a small uh, order of filter. And if we have the capability of implementing a higher order filter, then we can see that we are able to retrieve the original waveform. I mean, our retrieved waveform is very close to the original waveform, and that means that even with even with changing background noise and all the noisy behavior happening in the background, the laptop or whatever device is implementing this Wiener filter can deliver the speech signal very cleanly and accurately. I mean, as shown in this illustration. So the order of filter actually determines the adaptability properties of the filter, how fast it can adapt to the changing scenario. And then the order of filter is a design parameter, because it is based on how much computational capable our DSP chip is. So these kind of parameters are taken into account when designing an adaptive filter and working with these kinds of filters. This basically completes our discussion. This is what I wanted to cover from the technical point of view in this webinar. Let's check out or let's discuss some job roles which are present in current market. So whoever wants to study this field and or work in this field, what are the job roles and responsibilities which are present in the current industry? So the first of the jobs will be a system engineering job. The system engineering job or career involves hardware design, not just hardware design, hardware and software design of DSP blocks, of complex signal processing algorithms or modems. Like one example is the modem. We have modems in our tablets, in our phones, which implement very complex signal processing algorithms, and there are hardware accelerator blocks and software algorithm, DSP algorithms running on them, and these needs to be designed and optimized and based on the requirements. So system engineering or system engineer is one who does all these kind of system design. So the other job role will be embedded firmware development. So once the system engineer has designed some algorithm to achieve some processing on the discrete signals, it has to be implemented on the chip. And embedded DSP firmware developers are the ones who will do that. So they have the knowledge of DSP algorithms plus the embedded software development, like embedded C development or embedded assembly language development, how the code should be written so that the processing is optimized from the code point of view. So that is also a very hot career option in DSP. Then we have layer one software development, where we have to understand the DSP algorithms and DSP concepts running. Like in communication field, we have L1 layer developers. We have L1 layer. We have a L1 layer in communication devices, which basically takes decisions based on different inputs to the layer from the physical layer. So physical layer provides information to the L1 layer, and L1 layer takes certain decisions, or whether we have to switch from one base station to another base station when we are moving in the area. So these kind of decisions are taken from the higher layers, and the higher layer developers have to have a very good understanding of DSP algorithms and DSP concepts. So that is one of the jobs. Then we have digital design engineering career options. So this is a multidisciplinary career option, where you have to understand the DSP concepts and the DSP requirements. Plus, you have to understand how to design the hardware. So you have to know VLSI design concepts also, how you write a RTL code, and how do you simulate hardware, and all those concepts are required. So this is also a very lucrative career option for somebody who wants to work in DSP domain. Then we have test automation and SQA engineers who continuously design test vectors or test scripts to break or to test all corner scenarios which can be involved in the DSP algorithms implemented. So we have some modem or DSP system, and the test engineer's job is to write scripts so that it can trigger or excite all the corner cases and important test scenarios, and see the result is coming as expected or not. So they also have to have a very good understanding of the DSP algorithm and concepts, and whatever domain they are working in, either in speech or in multimedia or image processing, or whatever domain they are working in. So these are some of the jobs, some of the important or highlighted jobs in the DSP domain. And some of the major companies which are offering these kind of jobs and which are working on DSP applications across numerous engineering branches and fields. I've tried to list down a few of the famous and big companies which are working in this domain. So the Qualcomm, so I have listed here the vertical. In the vertical, we have different domains. So one is cellular modem technology, which powers your smartphone and all. Then we have Wi-Fi modem technology for the connectivity. Then we have DSL, which is the broadband technology. We have Bluetooth. We have wearable solutions, smartwatches and smart devices. We have navigation solutions for location and positioning. We have biomedical solutions. There are lots of biomedical devices and applications right now. Then we have radar devices and radar application. We have multimedia. We have speech and audio application and machine learning applications. And the companies, a few of the companies who are working in these branches and fields are Qualcomm. Qualcomm, Intel, Apple, and Samsung are basically working in most of these branches. The cellular modem tech is Qualcomm's primary industry. Then Wi-Fi, Bluetooth, wearable solution, navigation, multimedia, speech and machine learning. Same for Intel. Intel has recently exited the cellular modem technology. Uh, but it is working in all of the other domains which utilizes DSP applications and extensive DSP algorithms. Then Apple is starting in cellular modem tech. I think from last 2 years it has started developing its own cellular modem. It was in news, and it already has their iWatch and their navigation technology, and Apple works in machine learning plus DSP applications by, I mean, it has a huge number of application on its device which uses machine learning plus DSP. Then Samsung works in all of these technologies. Mevnir, I know, works in cellular modem tech. MediaTek works in cellular modem plus speech and audio and multimedia for their uh, uh, smartphone chips. So like Qualcomm has Snapdragon, MediaTek has Helios, uh, Samsung has Exynos. All these chips are very high computing power chips, and they have very high DSP cores. Radisys, Rakuten, and are also working in cellular modem tech. Then there is Broadcom, which is not working in cellular modem, but the other wireless and wired communication technologies. Marvell is one of the very good companies working in Marvell Semiconductors, which is working in Wi-Fi and cellular modem. Then there are dedicated companies for the speech and audio signal processing, like Harman, Bosch, and Mercedes, uh, where they work for the speech for their speakers and like their sound systems, speaker systems, and all. Then we have DSP service based, or I mean, not service based, like NI is National Instruments. They develop products, software based products to do very complex signal processing applications, write scripts, and simulate um, end-to-end link level simulation of complex systems, like the whole cellular modem system or 5G technology simulation, 4G simulation, Wi-Fi simulation. So NI provides such products. Then there is a Texas Instrument which builds hardware for these applications, cellular and Wi-Fi modem. So the Texas Instrument provides some of the career option for DSP. There is MathWorks, which has a very famous product called MATLAB, and MathWorks provides application, or it has products which are, I mean, different toolbox of MATLAB, which are there for every technology. I mean, whatever technology you can think of, there is a toolbox in MATLAB for that. Then there is MaxLinear, which is also working in cellular and wireless modem technology, developing hardwares for the modem technology and working in the machine learning and speech and audio processing. So these are few of the major companies working in on DSP application. There are many more companies which are working, and many more technologies which are using DSP. But I felt these are some of the most important ones, and that's why I mentioned here. I think this completes my presentation and whatever I wanted to cover. I think I've taken a little bit more time, but yeah. So this is all that I wanted to cover in this webinar. I hope I could do justice and explain the concepts clearly. So
Yes, Mr. Pavan, thank you so much for an informative session. Like I got many feedbacks from the participants that this session was really nice and informative and all. So thank you so much for walking us through it. So participants, feel free to drop your questions on the chat box.